In 1977, NASA launched two machines named Voyager, built to survive 5 years. 48 years later, both are still transmitting from a place neither was designed to reach. Scientists confirmed the crossing in 2012 and then argued about it for another full year. Not because the data was unclear, because two sensors bolted to the same spacecraft read two different signs of the same boundary. The wall sat 1 billion miles farther out than every model predicted. Voyager 2 crossed that same edge nearly 1 billion miles closer than its twin, and the one reading every scientist trusted to prove a crossing. The direction of the magnetic field pointed exactly the same way for another full year. Tonight, we go through 7 discoveries at that edge. A wall 2 spacecraft couldn't agree on, a sound recorded where no air exists, a highway that let radiation cross both ways before anyone agreed a border existed, a boundary that gave way in days after 35 years, a second machine that measured what the first one's broken instruments missed, a region hotter than physics allowed, and a ribbon of light no equation predicted. The first discovery was a disagreement, so was the last one. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. Voyager 1 and Voyager 2 left the same clean room, calibrated against each other so precisely that engineers trusted their instruments to agree on almost anything, decades apart, without argument. Both went looking for the same boundary. The termination shock, the place where the solar wind, moving faster than 1 million miles an hour since it left the sun, finally slows below the speed of its own pressure waves. Voyager 1 found it in December of 2004, 94 times farther from the sun than Earth is. Voyager 2 found a version of the same wall in August of 2007 at only 84 times that distance. Same star behind them, same wind carrying them, same instruments, reading the same physics. Nobody had built a bubble that could do that. For a while, the easier explanation was instrument drift. Recalibrate the sensors, blame 4 decades of radiation, and the numbers might yet fall back in line. But recalibration never closed the gap. 2 machines, cross-checked against each other before launch and monitored for drift every year since, simply were not lying to anyone. Models drawn before either spacecraft arrived couldn't even agree with each other, spread across a range wide enough to swallow the entire orbit of Uranus. Then 2 real machines went and found 2 real, different answers of their own. A gap nearly the width of Saturn's own distance from the Sunday. Picture someone walking into a strong headwind, coat billowing loose behind, pressed flat against the chest in front. That is roughly the shape our sun's own wind makes, moving through the galaxy. And the 2 spacecraft happened to leave through 2 different folds of that coat. 16 days and 30 years of travel apart. You have spent every night of your life inside a bubble that isn't the same thickness in every direction. Thinner on the side that leads, thicker on the side that trails, dented wherever the galaxy leans against it hardest. And nobody drew it that way on paper until 2 machines found out by accident. The edge kept saying something different every time we asked, and this was only the first time we asked. Could 2 instruments, calibrated against each other this precisely, really disagree about something this basic? They did, and that disagreement is only the first of 7 tonight. What does a boundary actually sound like? If you could stand close enough to hear it ring, how does an edge that took 35 years to approach give way in a matter of days? Why would the coldest region anyone had ever described turn out to run hotter than the surface of a star, and the bright ribbon of light wrapped most of the way around us? What is it, if no equation ever predicted it? Each of those questions gets answered tonight, roughly in the order the 2 machines actually found them. But the asymmetry itself was never simply a curiosity about geometry. Something was pressing harder on one side of that coat than the other. And whatever it was did not come from anywhere inside our solar system at all. 2 years before the crossing, scientists now treat as official, An argument had already broken out inside the Voyager team. In 2002, and again in 2003, the cosmic ray detector aboard Voyager 1, the instrument overseen by physicist Frank McDonald, returned readings his group was confident enough to call the termination shock itself, confident enough to submit for publication. But a separate instrument on the very same spacecraft, the charged particle detector overseen by Stamatios Krimigis, disagreed. His team's data showed no such crossing at all. Two groups of scientists, staring at two instruments bolted to one machine, reached opposite conclusions about whether history's first crossing of this boundary had already happened. The disagreement ran for the better part of 2 years before the real shock, in December of 2004, finally settled it. The 2002 signal turned out to be a pressure wave from the Sun, washing back across a region the spacecraft was already skimming, close enough to the true boundary to fool one instrument without the spacecraft having crossed it yet. Neither team was careless. Neither was reading their own numbers wrong. They disagreed because the region in front of a boundary this large does not behave like a line on a map. It behaves like a shoreline in a storm, the water reaching further up the sand on some waves than others, so two observers standing a short distance apart could each honestly report a different edge to where the ocean ends. For 2 years, part of the scientific community believed humanity, and by extension you, had already reached interstellar space, based on data from a machine that had not yet arrived. The quiet correction, when it finally came, travelled far less distance than the headline it corrected ever had. The way a retraction printed on page 9 never reaches the readers who saw the original claim on page 1. What the false alarm revealed mattered more than the error itself, a boundary layer turbulent enough, even before the true shock, to send a pressure wave rippling backward across tens of millions of miles, strong enough to mimic a crossing from a machine that hadn't reached it yet. A calm, static wall does not do that. Only a wall already flexing under uneven pressure sends false signals of itself ahead of its own arrival. The boundary, in a sense, had practiced lying to us once before it finally told the truth. 2 working instruments, 2 careful teams, 1 honest disagreement. And the argument itself turned out to be the first real data anyone had about how turbulent the true crossing would be. The mission never forgot the lesson. From that point on, no crossing at this boundary would ever be announced on the strength of 1 instrument again. A rule that would matter far more a decade later, when an entirely different disagreement broke out over what to call the region on the other side. You would have had no way to tell, watching the numbers arrive in real time, which of the 2 teams to believe. Neither was wrong about what its own instrument showed. Only the meaning of the crossing itself was still genuinely undecided. Every textbook diagram of the heliosphere used to include a second curve out past the tail entirely. A bow shock, the same kind of wave a boat throws up in front of its hull, formed because our sun was assumed to be ploughing through the interstellar medium faster than the medium's own pressure waves could clear out of the way. It was standard physics, applied confidently for the better part of 5 decades to a wind nobody had ever actually measured from outside. But nobody had actually measured that wind from outside until long after the diagrams were already printed. Then, in 2012, a team led by physicist David McComas, the same scientist who would later lead the mission responsible for tonight's final discovery, recalculated the sun's true speed relative to the surrounding interstellar gas, using better data on the direction and strength of the local interstellar magnetic field. The true relative speed came back slower than every prior estimate. Slower by enough that no shock forms at all. What the field does instead is drape gently around the leading edge of our solar system, the way water bends around a slow-moving stone rather than exploding into a wake behind a speeding one. Not a subtle correction. An entire named feature, printed in decades of diagrams and planetarium shows, quietly removed from the ones printed after 2012. A bow shock, if it existed, would mean our solar system announces itself to the galaxy the way a fast boat announces itself to a still lake. What forms instead is a far quieter signature. A gentle compression with no sharp front, closer to the way a slow swimmer displaces water without ever raising a wake. For 50 years, we described our own arrival in the galaxy as louder and more violent than it has ever actually been. Now add what that correction actually cost. Every planetarium model, every printed diagram, every documentary illustration built before 2012 had to be quietly retired. Not because a dramatic new observation revealed the missing shock, but because the absence of a signal nobody found finally outweighed decades of confident drawing. Nothing about our solar system's actual passage through the galaxy changed the day the correction was published. The wind had been behaving this quietly all along. Only the diagram had been wrong, confidently, for 50 years. A reminder that the loudest-looking feature on a map is not always the one that turns out to be real. Every version of that diagram you were ever shown, in a textbook or a documentary, was carrying an error nobody had actually measured yet, quietly, your entire life, until 2012 finally caught up to it. The idea itself was not new. Physicist Eugene Parker had described the general shape of a star's wind pushing against interstellar gas back in the 1950 seconds, decades before any spacecraft existed that could test it. He was right about the wind. The specific, dramatic shockwave riding ahead of it, added by later modelers filling in a gap Parker's own equations left open, was the part that would not survive contact with real data. Parker did not live to see the correction published. He died in 2022, having spent a career watching his own predictions about the sun outlast most of the embellishments other scientists later built on top of them. Both Voyagers carry their magnetometers at the end of a long boom, extended away from the spacecraft body specifically so the sensor wouldn't confuse its own readings with the electronics humming a few feet away. The instrument and the boom carrying it were designed under physicist Norman Ness, who had already built magnetometers for several earlier NASA missions by the time Voyager launched. Experience that still couldn't guarantee what happened next. That boom had to unfold correctly, joint by joint, in the vacuum of space, with no astronaut and no repair mission available if it jammed even slightly out of alignment. It unfolded correctly on both machines, decades ago, and has needed no intervention since. Every claim in tonight's episode about a magnetic field that failed to rotate, a field that kept climbing beyond the wall, a field pointing in directions no model predicted. All of it depends on that one uninspected joint having locked into place correctly on the first and only attempt it would ever get. There was no way to test that specific joint under the specific cold and radiation of 4 decades in deep space before committing it to a flight with no return trip. Engineers built the best approximation they could on the ground, watched the mechanism unfold correctly a handful of times in a lab, and then trusted the design to a version of itself they would never inspect again. Had that boom jammed even part way, mission planners had no secondary mechanism to force it open. No backup boom, no repair option, nothing but the single mechanical attempt built into the original design decades earlier. Elsewhere on both spacecraft, sensors have degraded, gone silent, or returned readings engineers eventually stopped trusting. The ordinary attrition of hardware operating this long, this far from any repair, the magnetometer's survival was never guaranteed. It simply happened to be one of the pieces that held, and an entire chapter of tonight's episode exists because of it. But Voyager 1's own plasma instrument, built by a separate team entirely, was not so fortunate. Damaged decades earlier, long before it ever neared this wall. That single failure, on a different sensor built by different hands, is a thread this episode picks back up later, once a second machine finally reached the same boundary carrying an instrument that still worked. No two instruments on either spacecraft have ever aged the same way, and nobody chose in advance which ones would still be listening when it mattered most. Reliability at this distance is not a specification. It is a bet, made once, decades in advance, that a specific piece of folded metal will still remember how to unfold after 40 years of cold, nobody could fully simulate beforehand. The engineers who built it moved on to other careers, some to retirement, long before the joint they folded by hand ever had the chance to prove them right. Everything you have heard tonight about a field that failed to rotate or kept climbing past the wall rests on a bet you never knew was being made decades before you were listening. Cross the termination shock, and the textbooks used to promise something almost restful, a becalmed layer. The solar wind slowed and settled, coasting the rest of the way to the true edge in one long, gentle exhale. But that is not what either spacecraft found. What they found, once researchers finally modeled the readings in full, was a region closer to a pot of water right at the point before it boils, riddled with magnetic bubbles tens of millions of miles across, pinching off from the solar wind's own tangled field lines and drifting through the heliosheath like foam. The bubbles form the way a soap film pinches into individual bubbles when disturbed. The sun's magnetic field, wound into a long spiral by its own rotation, becomes so twisted at this distance that it starts snapping and reconnecting on itself, shedding vast detached loops rather than holding one clean shape. Some models suggest more than half this layer, by volume, may be made of these disconnected pockets. Each bubble, individually, is larger than the orbit of the Earth around the Sunday. Voyager 1 would have needed the better part of a year, at its own considerable speed, simply to cross from one side of a single bubble to the other. Let that settle for a moment. Something larger than Earth's entire orbit, adrift and unnamed, until a supercomputer finally modeled it in 2011. Now picture your own breath fogging a cold window, not a flat sheet of mist, but a mass of overlapping, jostling droplets, none of them quite touching the one beside it in a clean line. That is closer to the texture of the region people picture as past the edge of the solar system. Not a wall you pass through and then relax. A froth to cross. The astrophysicist Merav Ofer led the team that first modeled this, after running the interaction on a supercomputer for months, expecting a tidy result and getting a foam instead. Buried in the same paper was an unexpected piece of good news. A layer this turbulent may trap and deflect a portion of the cosmic rays that would otherwise reach the inner solar system directly. The very froth that ruined 50 years of clean diagrams may also be doing a small, uncounted share of the work of keeping the space around this planet a little safer than it would otherwise be. You will fall asleep tonight inside the calm half of that same field, the half that never twisted far enough to snap. Nothing about that mercy was engineered. It is simply where, on the enormous scale of this froth, this small, warm planet happened to end up sitting, closer to a specific accident of position than to any promise the universe ever made. A few million miles the other way, and the froth itself would have been this planet's story instead. Nobody chose this particular pocket of calm for you. It was simply where the numbers happened to land, the way a coin happens to settle on one face rather than the other. Every model of the termination shock made the same prediction. The solar wind, slammed from a supersonic gale to a subsonic drift, should convert most of its lost speed directly into heat, the way a car's brakes turn motion into warmth at the disk. It is simple, well-tested physics, confirmed in 100 other astrophysical shocks throughout the galaxy. When Voyager 2's plasma instrument, overseen by physicist John Richardson, finally measured the actual temperature at its own crossing in 2007, the heat was there, but only a fraction of what the energy budget said it owed. Roughly 3/4 of the energy the solar wind should have converted into warmth was simply unaccounted for in the plasma itself. The leading explanation is not comforting in its simplicity. The missing energy did not vanish. It went somewhere models hadn't been built to track, funneled instead into accelerating a small population of particles to extraordinary speeds, a shortcut around ordinary heating that few researchers had built into their equations beforehand. A wall that was supposed to convert motion into warmth converted a working majority of it into something closer to a slingshot. Picture a car crash where 3/4 of the energy that should have crumpled the hood instead went into hurling a single seatbelt buckle clean through the windshield, leaving the rest of the vehicle strangely, disproportionately intact. That is roughly the shape of the imbalance once investigators checked the numbers against what the crossing should have produced. Some of those accelerated particles escaped back into the inner solar system entirely, meaning a fraction of the highest energy particles occasionally reaching Earth's own magnetic field and passing through the air above you tonight may have been forged at exactly this wall, flung backward across billions of miles by a process that still doesn't fully add up on paper. Both spacecraft crossed the same kind of wall at different points on its uneven surface, and both returned versions of the same missing heat. Whatever is stealing that energy is not a quirk of one crossing. It is built into the physics of the boundary itself. Here, then, is the first honest answer tonight. The wall disagrees with itself because it was never held up by our sun alone. The false alarm, the vanished bow shock. Every discovery so far belongs to a boundary shaped by a negotiation. The outward pressure of the solar wind pushing against something pressing back from outside, harder on one side than the other. That outside pressure is the interstellar medium itself, the thin gas and magnetic field of the wider galaxy, leaning against the bubble that holds your entire solar system together. That is the first layer of the answer. It is not the whole one. Now add what nobody expected once scientists started measuring that outside pressure directly, year after year. It is not holding steady. Both spacecraft, on opposite sides of the sky, have recorded the same rising trend in the strength of that outside field for more than a decade after their crossings. A climb neither one has found the end of. Whatever is leaning on our solar system from outside is not simply constant. It may be building. We still don't know why, and two machines are still out there right now, on opposite sides of the sky, gathering more of that answer than we have room to explain yet. There is no instrument on either spacecraft that measures the density of the thin gas around it directly, the way a thermometer measures heat. The plasma out there is far too sparse for that. Sometimes fewer than one charged particle in an entire cubic foot of space. Instead, the instrument built by Donald Gurnett's team at the University of Iowa listens when a shockwave from a solar storm, having taken the better part of a year to travel outward, finally slams into the surrounding plasma. It makes the plasma ring the way a struck bell rings at a pitch determined by its size and material. From the pitch of that ringing, and only from that, scientists can calculate exactly how dense the plasma around the spacecraft actually is. The instrument itself is almost absurdly simple for what it accomplishes. Two thin metal antennas, each about 30 feet long, extended from the body of the spacecraft like a pair of stiff wire whiskers, tuned to catch the electric field oscillations the plasma produces once disturbed. No moving parts. No lens, no dish, nothing that could be pointed or aimed. Just two wires, listening in whatever direction the spacecraft happens to be tumbling. Gurnett had built instruments for 6 previous NASA missions by the time this one returned its first strange signal, but he did not expect what came back to be, in the most literal sense, audible. When his team converted the electric field oscillations into a sound file and played it back, what emerged was a rising, alien tone, an actual recording of interstellar space, captured decades after launch by a machine that was never designed to make a sound at all. NASA released the clip publicly within days, and it spread further and faster than almost anything else the mission had produced in 35 years, because it asked nothing technical of the listener at all. You did not need to understand plasma physics to feel something listening to it. Pause on that. Somewhere in an archive, there is a real audio file you could listen to tonight, made from something no human ear has ever stood close enough to hear directly, that documents a wave passing through the space beyond our Sunday. Gurnett would spend nearly 6 more decades on the mission after building that first instrument, retiring only in his late 80s, having outlasted most of the hardware he had once helped design for what was originally billed as a 5-year errand to 2 planets. He died in 2022, 2 years after the discovery this episode turns to next. One he had spent nearly 50 years listening for without knowing, until the very end of his career, that it was even there to hear. The instrument he built in the 1,970 seconds to catch one shockwave every few years was, without anyone intending it, also capable of catching something that never went silent at all. It simply took 4 decades, and someone willing to look before anyone noticed. For years, the ringing only ever appeared after a solar storm, a single, dramatic event, arriving roughly once every few years, giving scientists one brief window to calculate the density before the plasma went silent again. Then, in data gathered across 2017 and 2018, a research team led by Stella Koch-Ocker found something that should not have been there at all. A faint, continuous oscillation present in the data almost constantly, with no storm required to trigger it. The interstellar medium, it turned out, is not the inert vacuum it plays in most descriptions. It hums, quietly, on its own, all the time, a low background activity nobody had a name for before this discovery. Still not fully explained by any existing model of how a nearly empty plasma behaves when nothing is disturbing it. The leading guess treats it as the plasma's own natural oscillation, excited continuously by a faint stream of low-energy electrons drifting through it. But a guess is still what it is, years after the paper describing it was published. What the hum actually gave researchers mattered more than its cause. A continuous rather than occasional way to measure the density of the same space you are drifting through in your sleep tonight. For years, scientists could only check the thickness of the space around Voyager, once every few years, whenever a distant storm happened to ring the bell. With the hum, they can check almost constantly, filling in a record that used to have long gaps in it with something closer to a running line. Stella Koch-Ocker was a graduate student when she first noticed the signal sitting in the data. A small and constant hiss she initially assumed was instrument noise, the kind of artifact every researcher learns to filter out before it wastes anyone's time. It took repeated checking across separate stretches of data collected months apart before she trusted that the hiss was real, present, and coming from outside the spacecraft rather than from anything wrong with the instrument reading it. She was reading data that had already crossed the boundary described earlier tonight, gathered by a machine older than either of her parents, and found something in it that 4 decades of prior analysis had filed away as background noise. Nothing about the hum required new hardware, a new mission, or a new spacecraft. It required only someone willing to look again at numbers everyone else had already decided meant nothing. Not silence with occasional noise, a hum underneath everything that was already there before anyone thought to listen for it. An entire property of the space just outside your own solar system, sitting unnoticed in decades of archived data, until a graduate student refused to assume it meant nothing. The discovery of an entire, previously unknown property of interstellar space began, in the end, as one person's decision not to dismiss something that looked, at first glance, like nothing at all. But before Voyager 1 ever crossed into that steady, endless hum, it spent more than a year inside a region so strange that scientists could not even agree, in real time, on whether the spacecraft had left the solar system at all. In May of 2012, the readings coming back from Voyager 1 changed so fast that some scientists on the team assumed, for a moment, that an instrument had failed. The count of low-energy particles native to our own sun collapsed to less than 1,000th of what it had been days earlier. At the same time, the count of high-energy cosmic rays arriving from the wider galaxy, particles the sun's magnetic field normally deflects and filters out, surged to nearly double its usual strength. 2 entirely different populations of particles traded places within a matter of weeks. The clearest sign anyone had ever recorded of a spacecraft passing through the true border of its own solar system. By every model published up to that point, that trade should have been the whole story. But it was not. The one measurement every scientist had agreed, years in advance, would confirm the crossing beyond doubt was the direction of the magnetic field itself, expected to rotate from the sun's orientation to the different, ordered orientation of the wider galaxy's field the instant the spacecraft passed through. The field did not rotate. Not that month, not the following month. For more than a year after the particle counts had already flipped, the magnetic field Voyager 1 was flying through kept pointing in exactly the same direction it always had, as if the spacecraft had not actually left anywhere at all. Not a clean threshold. Not a single agreed-upon hour. Teams within NASA split over what to call the region. Some argued Voyager 1 had already reached interstellar space and the field would catch up to the models eventually. Others argued that a true crossing, by definition, required that field to turn, and until it did, the spacecraft was still... Reporters wrote premature headlines announcing an exit from the solar system, only for mission scientists to walk the claim back publicly, more than once, because their own instruments would not agree with each other, not because the instruments disagreed on the facts, because the scientists reading them disagreed on what a crossing was even allowed to mean. Here's the part that changes everything. The region Voyager 1 was flying through let particles cross freely in both directions, solar particles leaking out, galactic particles leaking in, while the magnetic field itself stayed anchored to home. Scientists eventually gave it a name that sounds almost gentle for something that caused over a year of professional argument: the magnetic highway, a road that let traffic move both ways, long before anyone could agree which country it actually belonged to. Edward Stone, the mission's chief scientist since 1972, refused to declare the crossing complete based on the particle data alone. No matter how dramatic the shift looked on paper, no matter how much pressure built from outside the project to announce a historic first. He had watched enough uncertain readings resolve into ordinary explanations over 4 prior decades to trust a headline over a field direction. He waited for the one number that mattered to him. And for more than a year, that number simply refused to move. If you had been the one deciding what to tell the public that year, you would have had the same 2 contradictory readings he did, and no way yet to know which one to trust. The instrument responsible for the first half of the trade, the cosmic ray subsystem, had been counting particles since 1977 without a single moment of the drama it recorded that May. In the days surrounding the crossing into the magnetic highway, the flow of particles born in our own sun's atmosphere dropped from a steady baseline to less than 1/1000th of its normal rate. Not a decline, a collapse, compressed into less time than it takes a season to change on Earth. Simultaneously, the instrument's separate channel for galactic cosmic rays, particles flung out by exploded stars elsewhere in the galaxy, long before our sun existed, climbed to nearly double its typical count, a rise the team could plot almost day by day. 2 populations, moving in opposite directions, on the same instrument, in the same short window. The kind of clean, simultaneous, unambiguous signal that in almost any other branch of physics would have ended the debate on the spot. But it did not end this one, because a single instrument, however precise, was never going to be allowed to declare humanity's first exit from its own solar system on its own. The rule the mission held itself to was not caution for its own sake, it was proportion. A claim this large, about a threshold this singular, required more than one line of independent evidence pointing the same direction before anyone was willing to put it in a headline. Being right on the first instrument and wrong on the second would have cost the mission more credibility than waiting ever could. So the team waited, publicly, for a second machine to confirm what the first one had already all but proven. Now consider how strange this particular kind of proof actually is. A machine built in the early 1970 seconds, using electronics that would be considered primitive before most people alive today were born, produced a measurement so exact that professional scientists could argue over its meaning for more than a year without ever once doubting the numbers themselves. The argument was never about whether the instrument worked. It was about what a boundary this large was even allowed to look like. The instrument is still running today, still counting the same two populations on a spacecraft now well over 100 times farther from the Sun than the Earth is. Every value it has ever returned, from the calm decades near Jupiter to the violent trade recorded in 2012, sits in one continuous, unbroken record, the longest single data set of its kind that any species has ever collected about its own solar system. No successor instrument, however advanced, will ever be able to fill in the decades this one already covers. Continuity, once broken, cannot be brought back at any price. Somewhere in mission archives sits a nearly 50-year printout of these two populations, rising and falling together, older than you are, a single graph line that has quietly outlived the careers of nearly everyone who first calibrated the instrument that drew it. You have never lived a single day this instrument wasn't already counting on your behalf. In the days immediately before the crossing, scientists now treat as final, the particle counts did not move in one clean, permanent step. They surged toward interstellar values, retreated partway back toward the old solar readings, then surged again. A stutter repeated at least twice before settling into the pattern that never reversed. For a machine moving in only one direction, at a steady speed, that back and forth made no obvious sense unless the boundary itself was doing some of the moving. But nothing about a spacecraft's own steady motion could explain a reversal like that. The likely explanation borrows from something already familiar, much closer to home. Earth's own magnetic boundary with the solar wind flaps and folds constantly. In response to gusts arriving from the Sun, rather than holding a fixed shape at any given moment, satellites orbiting the same Earth you are lying on tonight cross that flapping boundary routinely, sometimes several times in a single day. The heliopause, scientists now suspect, does something similar on a vastly larger scale, folding briefly inward, releasing, folding again before the underlying pressure balance finally settles enough to hold one position. A satellite flickering across Earth's boundary several times in a day is a known, almost routine event. A boundary tens of billions of miles wide doing the same thing, even briefly, means the edge of an entire solar system was folding and unfolding on a timescale of days, vast beyond ordinary description, and still, on its own scale, moving like something breathing rather than something fixed. For the scientists watching the data arrive in real time, each retreat looked, for a moment, like proof the whole crossing had been a false alarm, exactly the kind of pattern that had already fooled one team back in 2002. It took the final, permanent surge, holding steady past the point where the previous ones had reversed, before anyone dared trust that this time the door had actually stayed open. No model published before the crossing predicted this particular stutter, because no model had reason to expect the last few days of a 35-year journey to be its most uncertain moment. The smoothest, most confidently drawn part of any diagram, the single clean line marking where one region ends and the next begins, turned out in practice to be the part reality was least willing to draw cleanly. Only in hindsight, months later, once the full record of readings had been laid out end to end, could anyone say with confidence which surge was the real one. In the moment, watching the numbers arrive one data point at a time, there was no way to know a false door from the true one until it had already stayed open far longer than any of the previous attempts. The last boundary of the solar system did not close behind Voyager 1 like a door. It fluttered shut several times before it finally stayed. What finally proved it had stayed open did not come from the particle counts, and did not come from the magnetic field. It came from an entirely different instrument. The one built to listen. The same one you already met a few minutes ago tonight. An outburst from the Sun in October of 2012 sent a shockwave racing outward at roughly 1 million miles an hour. It took the shockwave about half a year to cross the distance. Voyager 1 had spent 35 years traveling. When it finally reached the spacecraft in April of 2013, It rang the surrounding plasma like a bell, and the pitch of that ringing gave scientists, for the first time, an actual density measurement for the plasma on the far side of the boundary. The number the magnetic highway argument had been missing all along. The plasma was roughly 40 times denser than the solar wind. Voyager 1 had been flying through for decades, not a gradual thickening spread across months of travel. A single, dramatic jump, confined to a boundary layer scientists eventually calculated at only a few astronomical units wide, a wall crossed in a matter of days after a journey 11 billion miles long. Imagine walking down an empty hallway for 35 years and stepping in a single stride into a packed stadium. Not a threshold you ease across, one you are simply, suddenly, on the other side of, with no memory of the stride itself. Working backward from that one number, the team pinned an actual date on the crossing for the first time, August 25th, 2012, nearly 8 months before the data that proved it had even reached Earth. Voyager 1 had already been sitting in interstellar space, sending signals home for the better part of a year before anyone alive could say so with certainty. The spacecraft itself never noticed the difference. Only the species waiting on its signal did. Radio waves travel at the speed of light, and even at that speed, a message from Voyager 1 already took over 16 hours to reach Earth in 2012. But the confirmation took longer still, not because the light was slow, but because the shockwave carrying the answer had to catch up to a spacecraft that never stopped moving, arriving 5 months after the question was already, quietly, answered. We were the last to know something that had already been true for most of a year. About the one place in the universe we might have expected to know first. 3 separate clocks had to line up before anyone on Earth could say, with confidence, exactly when home had ended. The 35-year clock of the spacecraft's own journey, the half-year clock of a shockwave racing to catch up with it, and the 16-hour clock of light crawling the rest of the way back to a species that had, by the time it finally heard the answer, already spent most of a year not knowing. No other event in human history has required quite this particular arrangement of clocks to date it. A threshold crossed in an instant, confirmed only after a chain of delays measured in months, light hours, and decades layered one on top of the other. Every other historic first our species has ever recorded happened, and was known to have happened in roughly the same breath. Consider what almost nobody stopped to notice at the time. News outlets had already run the headline once, in 2011, when the particle counts first began to shift. Voyager leaves the solar system, printed a full year before the spacecraft had, by any measurement anyone could defend, actually left. NASA spent that year publicly, patiently, correcting its own good news, insisting the crossing had not yet happened, no matter how badly everyone wanted to report it. It is a strange position for an agency to hold, talking a hopeful public down from its own historic accomplishment again and again, because the one number that mattered most had not yet said yes. But when the plasma data finally arrived in the spring of 2013, and Ed Stone stood in front of reporters at NASA headquarters that September to confirm, at last, that Voyager 1 had genuinely left the solar system a year earlier than the announcement itself, several of the same journalists in that room had already written the sentence once. They had to write it again, more carefully this time, about an event that had technically finished happening while their first draft was still circulating. Stone, by then 81 years old and 41 years into a mission that was never meant to outlive its own decade, opened the press conference not with the headline everyone wanted, but with the same caution he had held to since 2011. This was a discovery about a boundary, he reminded the room, not a departure. The spacecraft had not left anything behind. It had simply gone somewhere. The mission's own founders, gathered around blueprints in the early 1970 seconds, had never seriously expected any machine of theirs to still be operating well enough to report from. He would go on to hold that same job. chief scientist of a mission that kept finding new boundaries to argue about, for another decade after that press conference, before finally stepping back from the role in 2022 at the age of 91. He died in 2024, having spent more of his life waiting on this mission's answers than most people spend on any single pursuit at all. Patient, by then, in a way the mission itself had trained him to be. Home did not end the moment we said it did. It ended quietly, months before, while we were still arguing about whether it could. And you, whoever you are listening tonight, were already living on the far side of that boundary before anyone told you so. Few scientists in any field ever get to watch a single question they helped ask at the very start of their career answered definitively decades later by hardware they themselves helped choose before either the answer or the argument over it existed. Stone got to watch it twice, once for each spacecraft, 6 years apart, and neither crossing agreed completely with the other. The two spacecraft he spent his career defending are still transmitting tonight, still crossing distances neither instrument will ever fully agree on the meaning of, in a conversation that has now outlasted the man who spent longest listening to it, and will likely outlast you as well. Bolted to the side of each spacecraft is a gold-plated copper disc, designed to outlast the machine carrying it by a margin longer than most objects our species has ever built. Encoded on it, greetings recorded in 55 languages, whale song, thunder, a mother's laugh, a baby's cry, and 90 minutes of music chosen to represent the range of a species whose builders never expected any of this hardware to still be transmitting from this far away. A simple diagram on the cover shows the positions of a set of pulsars, precise enough that whoever eventually finds it could calculate exactly when and from where the record was launched. The record plays on a cartridge and needle included in the package, along with symbolic instructions etched directly onto the cover explaining, without a single word of any human language, how to make it spin. Whoever built the instructions had to assume no shared alphabet, no shared number system, nothing at all in common with whoever might eventually attempt to read them. Only the same physics everywhere obeys. Nobody designed the record to be found. It was designed to be true, in case it ever was. It crossed the same magnetic highway, the same abrupt density wall, the same wind and foam and hum described tonight, sealed and silent, carrying music from a species that will very likely no longer exist in any recognizable form by the time, if ever, the committee that chose its contents, led by the astronomer Carl Sagan, had only months to decide what fraction of an entire species and its history deserved to survive the loudest, longest silence any human artifact has ever been sent into. They chose Bach over almost anything more famous. They chose a Georgian folk song, a Peruvian panpipe melody, laughter recorded from no one in particular. They chose, in the end, not the most impressive things a species had made, but the things that felt most honestly like being alive. You share a home with something that has already left it, carrying proof you existed, farther than anything you will ever personally go. And that, on its own, might be where an episode like this one is tempted to end. A golden disc, drifting past every wall this episode has described, carrying your species' best attempt at a goodbye. It would be a fitting place to stop, but it is not, quite, the place this episode actually stops. Sagan himself would not live to see either spacecraft reach the boundary this episode describes. Dying in 1996, 16 years before Voyager 1's crossing, and more than 2 decades before Voyager 2's, he helped choose what a species should say to the dark without ever learning whether the dark had anything resembling an edge, let alone what waited on the other side of it. He did live long enough to watch the record depart, to watch it clear each planet it was ever going to photograph up close, and to spend the rest of his own life defending, in public, the idea that sending it at all had been worth doing. Voyager 1 and Voyager 2 were designed, funded, and approved for a 5-year mission. Fly past Jupiter, fly past Saturn, and stop. But nothing in the original budget accounted for a machine still gathering data 3, then 4, then 5 decades later. The extension that let both spacecraft keep operating past their planetary flybys, formally approved in 1980 and renewed repeatedly since, was justified at the time, mostly on the grounds that turning off a still functioning spacecraft to save a relatively small annual budget line felt like a waste nobody wanted to be responsible for. Not because anyone in 1980 expected a 50-year argument with the edge of everything, because nobody could find a good enough reason to be the one who ended it early. Every discovery in this episode, the dented wall, the foam, the highway, the crossing, the hum, the heat, the ribbons still to come, was gathered by hardware that existed, technically, on borrowed time from the moment its original mission plan ended. Nobody who signed the original design documents in the early 1970 seconds was budgeting for a machine that would still be redrawing the shape of the solar system 50 years later. The formal name given to that extension, the Voyager interstellar mission, was itself a kind of quiet bet. A title assigned in 1980 to a phase of the journey that, at the time, existed only on paper, describing a boundary neither spacecraft had come anywhere close to reaching yet. That bet has now paid out on both counts. For both spacecraft, decades past anyone's original expectation, past the point where anyone still working the mission remembers it as a bet at all, rather than simply how things have always been. A 5-year errand became a 50-year argument with the edge of everything, funded one budget cycle at a time, by people who kept choosing, year after year, not to be the ones who finally let it go dark early. Nobody who approved that first extension in 1980 is still working the mission today. The commitment outlived the careers of nearly everyone who first agreed to make it, passed down like a promise nobody wanted to be the one to break. A mission is, in the end, just a promise a group of people make to keep paying attention to something for longer than any of them individually expect to be around to see it through. This one has now outlived several full careers and is still, tonight, being kept, on your behalf, by people you will never meet and could not thank even if you tried. Every few years, a newer, better-funded proposal has come along, competing for the exact line item keeping both spacecraft alive, and every few years, the older machines have won the argument again, on the strength of data no newer instrument could possibly replace, because no newer instrument has been running long enough to have collected it. A 50-year head start, once built, cannot be purchased by any amount of new funding. It can only be kept, one budget cycle at a time, or lost forever. Voyager 1's plasma instrument, the one built to measure the density of charged particles directly, had already failed in 1980, decades before it ever reached the heliopause, a casualty of a planetary flyby. Damaged during the close pass of Saturn, long before anyone knew it would matter this much later, which is the entire reason scientists had to wait for a distant solar shockwave to ring the plasma like a bell just to infer a number they could not read outright. But Voyager 2's matching instrument never failed. When the second spacecraft reached its own crossing in November of 2018, at a distance of roughly 14 billion miles from the Sun, it did something its twin never got to do. It measured the wall in real time. As it happened, with no bell-ringing workaround required, the direct numbers confirmed the indirect method beautifully, a relief the team allowed themselves only briefly, since agreement on the general principle did nothing to explain the disagreement in the details on the ground. They also revealed something the first crossing had not shown clearly at all: a boundary layer thicker and messier than the clean, narrow wall Voyager 1's data had implied, with hints that some of the Sun's own plasma was leaking past the official edge into interstellar space, mixing for a stretch before the two populations fully separated. The two spacecraft, 6 years and roughly 100 degrees of sky apart, had not found the same wall. They had found two different textures of the same idea. Here's what most people completely misunderstand about this. The heliopause is not a shell you could touch or paint or mark with a flag. It is closer to a negotiation, decided in real time, between the pressure of our sun's wind and the pressure of the galaxy pushing back, and the terms of that negotiation depend on where you happen to be standing when you check. The mission team deliberately waited months before publishing Voyager 2's numbers, cross-checking them against every model built from Voyager, one's more roundabout measurement, before committing either spacecraft's data to print. Two working instruments, aimed at the same fundamental boundary from opposite sides of the sky, 6 years and 100 degrees of sky apart, gave humanity its first real chance to check one crossing against another. The lesson was not that one number finally won. It was that a single crossing, however precise, was never going to be the whole story. Voyager 2 succeeded partly because Voyager 1 had already failed in exactly this one way. A second chance, built in part from the specific ways the first chance had already gone wrong. Neither machine, on its own, could ever have delivered the fuller picture both together finally did. Engineers reviewing the mission's history going into the second crossing knew exactly which instrument to watch most closely for signs of the same decay, because they had already watched its twin fail once, decades earlier, at a moment nobody back then thought would still matter this much. Once launched, neither spacecraft's course was ever meant to be corrected again for anything beyond the planetary flybys already planned. Voyager 1, still climbing, is heading in the general direction of a faint star called Gliese 445, and will pass within a little less than 2 light-years of it in roughly 40,000 years. Voyager 2 is heading toward a different star entirely, Ross 248, expected to make its own comparably distant, comparably silent pass in about the same span of time. Two machines, launched 16 days apart from the same small planet, are now permanently separating toward two different points of light, neither of which their builders selected on purpose, simply whichever star each spacecraft's already committed trajectory happened to be drifting toward once the last planetary flyby was complete. Nobody at either launch chose a destination star at all. The destinations chose themselves, decades later, out of whatever direction the math had already fixed. They will likely go dark decades before either encounter, drifting the rest of the way in perfect silence, carrying their golden records towards stars that have no idea anything is coming. 40,000 years is not a figure chosen for effect. It is longer than the entire span of recorded human civilization, repeated roughly 8 times over, and it describes only the moment of closest approach, a silent, uncelebrated flyby past a star with, as far as anyone currently knows, nothing there to notice it happen. But long before either arrival, both spacecraft will have gone dark, their transmitters finally too weak to be heard, across a gap that, by then, will have grown wider than either machine's entire journey through the solar system this episode has described. Now, layer on the part almost nobody stops to picture. Neither star is a chosen destination in any meaningful sense. Both are simply the nearest points of light. Each spacecraft's already committed path happens to be drifting past, decades from now, the way a leaf dropped into a river passes whatever bank happens to be nearest when the current finally lets it drift ashore. Nobody standing at either launch pad in 1977 chose Gliese 445 or Ross 248 for anything. The stars were simply wherever the math pointed once the last planetary flyby bent each trajectory for the final time. Neither star is visible to the naked eye from Earth, not even to you, looking up tonight. Two machines built by a species that once told stories about its destiny written in the stars are now drifting, in perfect silence, toward two stars too faint for that same species, and your own two eyes to have ever noticed without a telescope. Home did not just release two machines tonight, it released them toward two separate futures. on courses fixed before either one had even reached the wall this whole episode has been describing. A divergence decided by physics and momentum long before either spacecraft had traveled far enough for anyone to know it had already been decided. Neither trajectory can be corrected now. Whatever star each machine eventually nears, it will near alone. Two crossings, in two directions, roughly 100 degrees of sky apart, are the entire dataset humanity has for what is, by volume, one of the largest structures anywhere near us. Every textbook shape drawn between those 2 points is an interpolation, an educated guess filling in a gap thousands of times larger than the 2 thin threads of actual measurement running through it. Picture trying to describe the shape of an entire ocean from 2 thin strings pulled taut between its surface and its floor, one near a coastline and one near a distant reef, with nothing in between ever sounded, sampled, or seen. That is the honest scale of what 2 spacecraft, however historic, can actually tell you about a structure this large. That is roughly the ratio between what has actually been measured of our solar system's true boundary and what remains still pure inference. Every side of the boundary neither spacecraft happened to fly through, above the plane where the planets orbit, below it, facing directly into whatever lies opposite the direction we're traveling, remains entirely unmeasured, filled in only by extrapolation from the 2 threads we do have. NASA has studied, on paper, an idea called the Interstellar Probe, a spacecraft designed from the outset to reach and cross this boundary quickly, using modern propulsion rather than a decades-old design, repurposed after a planetary tour, instrumented specifically to answer questions the 2 Voyagers were never built to ask. No version of it has been funded to launch. Even in the most optimistic proposed timeline, it would still take decades after departure to reach the edge, arriving at a wall that will, by then, have had time to breathe in and out several times more since the last machine touched it. Even the 2 threads we do have were never intended as a survey. Both spacecraft were headed somewhere else entirely when they happened to cross this boundary. On their way out towards stars neither of them chose. The most complete measurement humanity has of its own solar system's true edge was gathered, in both cases, almost as a byproduct of a longer journey aimed at something else. A proper survey of a structure this size would send multiple spacecraft in multiple directions at once, purpose-built for exactly this question. What we have instead is 2 accidental data points, collected decades apart by machines with somewhere else to be, and an entire field of research built carefully, patiently, on top of them, one cautious inference at a time. Every planetarium show, every documentary, every illustration you have ever seen, confidently rendering the full bubble of our solar system in cross-section, is, technically, showing you an artist's best interpretation of a shape, backed by 2 needle-thin threads of hard data. It is not a lie, but it is simply far less certain than the confident rendering ever lets on. Nobody drawing that shape today has seen any more of it than the 2 Voyagers happened to fly through by accident. Decades ago, the sun's wind rises and falls in strength across its 11-year cycle, and the wall it holds up rises and falls with it. During periods of higher solar activity, the heliopause pushes farther out, the pressure from within winning more ground against the interstellar medium pressing on it from outside. The same negotiation described earlier tonight, simply tilted by a few more years of sunlight. During quieter periods, the boundary can retreat, in principle by a distance measured in billions of miles, before the cycle turns again and pushes it back out. What Voyager added was not the discovery of the cycle, which astronomers have tracked for centuries. It was the discovery that the cycle reaches all the way out to the edge of everything, flexing a wall 10 billion miles away in step with freckles of magnetic activity on the surface of a star. A map of the edge of the solar system drawn from Voyager 1's 2012 crossing, and a map drawn from Voyager 2's 2018 crossing were never going to agree perfectly. even setting the asymmetry of the bubble's shape aside. Because 6 years is more than half a solar cycle, and the wall the second spacecraft met was not required to be standing in the same place the first one had left it. Sunspots have been counted, cycle after cycle, for centuries. Long before anyone understood what that rhythm might be doing to a boundary nobody had yet reached. The sun is presently past the midpoint of a rise in activity, meaning that somewhere out past both crossing points, right now, the boundary is very likely still pushing outward, ahead of the last position either spacecraft actually recorded. But neither number in either published paper is the current number. Both are already historical the moment they reach print, describing a wall that has kept moving in the years since anyone last touched it. Hold that for a moment. The edge of your solar system has a pulse. It is not a boundary so much as a boundary that breathes in and out, on a rhythm longer than most human attention spans but shorter than a human life. And every published diagram of where home ends is, at best, a photograph of one single breath, already out of date by the time it reaches print. The edge kept saying something different every time we asked. Not because anyone was measuring it wrong, because the thing being measured genuinely does not hold still. No instrument currently exists to check the boundary's present position directly. Everything anyone can tell you about where the wall stands tonight is an extrapolation, built from 2 old crossings and a model of how the cycle should behave, rather than a fresh measurement of the thing itself. The next real chance to check will not come from a new crossing. It will come from decades of continued modeling, chasing a wall that will already have moved again by the time the refinement is finished. Picture the popular image of interstellar space. Cold, dark, still, the coldest kind of empty a mind can reach for. For decades, remote observations of starlight passing through the nearby interstellar cloud supported roughly that picture, estimating a temperature in the range of a chilly 6,000 or 7,000 degrees. Cold by stellar standards, unremarkable by the standards of a universe that runs far hotter almost everywhere else. Then Voyager 1 got there and measured the plasma directly. From inside it, rather than reading the shadow it cast on starlight from trillions of miles away. The number that came back was 3 to 5 times higher than the remote estimate. A genuinely hot plasma, by the standards of the thin interstellar medium, sitting in a region every prior model had described as one of the calmer, cooler stretches of the galaxy, a little over 30,000 degrees, hotter by that raw figure than the visible surface of many of the stars scattered across the sky above you tonight, carried by a gas so thin it could never scorch anything, in a place every prior description filed under empty without qualification. Not cold, not calm. The two measurements were not simply wrong against each other, they were measuring subtly different things, in ways researchers are still reconciling. But underneath the technical footnote sits a plainer discomfort. The one place in the universe most confidently described, in advance, as calm and empty and cold turned out to be none of those 3 things in quite the way anyone expected, the moment a machine actually stood inside it, instead of squinting at it from a distance. Temperature, out here, does not mean what it means standing in a room. A plasma this thin carries almost no actual heat. Standing in the middle of it, if such a thing were survivable at all, would feel like nothing resembling warmth, because there simply are not enough particles per cubic foot to transfer any of that motion to bare skin. The number describes how violently each rare particle is moving, not how much energy is available to cause a burn. It is possible, in other words, to be surrounded by something simultaneously hotter than a bonfire and colder than anything ever touched. A distinction the plain English word hot was never built to hold at the same time. Every word we have for temperature was built by bodies standing in rooms, near fires, under suns, where heat and density always arrive together. Out here, for the first time, that pairing quietly comes apart, And an ordinary word turns out to have been describing two different things all along, without anyone noticing until a machine finally went far enough to separate them. Every future estimate of this region will now have to account for both numbers, the old remote one and the new direct one, and explain why a single patch of space can honestly answer the same question two different ways depending on how you ask it. The interstellar magnetic field was supposed to settle into a fixed, ambient strength once a spacecraft was fully clear of the sun's influence. One number, steady, the background hum of the wider galaxy. Instead, the magnetometers on both Voyagers have recorded a field that keeps climbing. Years after the crossing, growing stronger and more uniformly aligned the farther the spacecraft traveled from the boundary they left behind. The rise was gradual enough that it took several years of accumulated data, compared carefully year over year before anyone trusted it as a real trend rather than noise in an instrument that had already been operating for far longer than its original designers ever expected. One proposed explanation treats the region just beyond the heliopause as a kind of pileup, interstellar field lines compressing against the leading edge of our solar bubble, the way snowbanks up in front of a plough, denser and more ordered the longer the plough has been pushing. The same coat in a headwind image from earlier tonight, simply measured in magnetic field lines instead of plasma density. It is a tidy picture, but it does not yet explain how far the compression should reasonably extend, or why the increase has continued for as long as it has, without leveling off the way the models predict it eventually must. Both spacecraft are still climbing through this same rising trend today, more than a decade after their respective crossings, sending back numbers that keep breaking the previous year's own record for how strong and how ordered the field has become. Nobody currently modeling the boundary can say, with any real confidence, at what distance, or even whether, the climb will ever finally level off. You've likely spent your whole life picturing outside the solar system as the plainest kind of nothing. A flat, undifferentiated, dark, cooling and quieting the farther you go. What both spacecraft are still sending back, years after anyone expected them to have left the interesting part behind, is a field that keeps getting louder rather than quieter, in a place every assumption said should have gone silent already. Every year without a plateau adds another data point to a trend line that keeps refusing to bend the way the tidy pileup model says it eventually should. At some point, if the climb never stops, the explanation itself will have to change, not just the numbers plugged into it. Whatever the true mechanism turns out to be, it is not a small effect confined to a narrow band just past the wall. It has now persisted across billions of additional miles of travel on two separate spacecraft, long enough to stop looking like a fluke and start looking like a genuine, unexplained feature of the space directly outside your own solar system. We still don't fully know why. Two machines are still out there, right now, gathering more of the answer than anyone has yet been able to explain. One faint, fading measurement at a time. Zoom out further, and there is a second boundary neither Voyager has come anywhere close to reaching. The edge of the local interstellar cloud, a modestly sized pocket of slightly warmer, slightly less dense gas that our entire solar system happens to be drifting through right now, and has been for at least the last few tens of thousands of years. Some researchers studying the cloud's edges suspect we may already be approaching, or even beginning to exit, the near side of it, a transition that would unfold slowly across a timescale of centuries to millennia, far too slowly for any instrument to catch in a single human lifetime, let alone a single mission. The measurement itself depends on watching the density of gas along many different lines of sight to nearby stars, then piecing together, indirectly, the outline of a structure no instrument has ever mapped from anywhere but inside it. The same fundamental limitation described earlier tonight about the heliosphere, simply repeated one boundary further out. If the sun does eventually drift into a denser patch of interstellar gas beyond this cloud, the heliosphere would be compressed further, its boundary pushed inward and Earth would sit slightly closer to a stronger flood of galactic cosmic rays than it does tonight. A slower, gentler version of the same squeeze that shaped the foam and the missing heat described earlier. Nothing about this feels imminent on a human clock, but everything about it is already, quietly, underway on the clock. The galaxy actually keeps, indifferent to whether any of it feels relevant tonight. The cloud itself is small by galactic standards, perhaps 30 light-years across, one modest pocket of slightly different gas among many scattered throughout this same arm of the galaxy, and our entire species, every war and every love song and every night anyone has ever slept beneath these particular stars has happened while passing through just this one unremarkable room in an unimaginably larger house. You are not simply resting inside a wind and a wall tonight. You are resting inside a moving cloud, inside a moving galaxy, drifting toward a border no spacecraft will ever reach in your lifetime, or several thousand lifetimes after it, and the drift does not pause for any of that to feel relevant. Nobody alive today will learn how the crossing actually unfolds, if it happens at all on the timescale current estimates suggest. Whatever language those future generations speak, whatever they call themselves, they will inherit a slightly different sky without ever having done anything to earn the change. No instrument built by any generation living now will still be operating by the time enough of the transition has unfolded to measure directly. Whoever eventually confirms it, if anyone does, will be working from evidence gathered by machines that do not exist yet, aimed at a boundary none of us will ever get to see arrive. The drift itself began long before either Voyager launched, and will continue long after both have gone silent. Neither Voyager took this next discovery. A far smaller spacecraft did, one that never left the neighborhood of Earth at all. Launched in 2008, the Interstellar Boundary Explorer does not fly to the edge of the solar system. It orbits our own planet and watches for something almost nobody had thought to look for: energetic, neutral atoms, particles born charged at the boundary of the heliosphere, that pick up a stray electron mid-collision, turn neutral, and then travel in a straight line, undisturbed by any magnetic field, all the way back to a detector near Earth. In effect, the instrument takes a photograph of the edge of home from 90-some astronomical units away, using messengers that need no engine and no fuel, only the accident of one electron changing hands at exactly the right moment. The mission cost a small fraction of what either Voyager originally cost to build and launch, and it never had to survive a single planetary flyby, a single decade of deep space radiation, or a single moment beyond Earth's own comfortable orbit. But small and cheap did not mean small and quiet. It photographed something two multi-billion-dollar spacecraft, hurtling directly through the structure itself, never fully captured. The whole shape at once, seen from a comfortable distance, rather than one narrow thread punched straight through the middle of it. The first full map the mission produced, in 2009, showed something that matched no simulation run before launch: a bright, winding band of concentrated emission arcing across a huge stretch of the sky, roughly twice as intense as the emission surrounding it, in a shape no team had predicted and no existing model of the heliosphere's boundary had room for. Scientists simply started calling it the ribbon because nothing in the literature already had a name for a feature like it. This was not a subtle statistical wrinkle buried in a footnote. It was an entire visible structure, wrapped most of the way around us. Sitting directly on top of the region every pre-launch model had left completely blank. The team spent the better part of a year checking their own instrument before they trusted the map enough to publish it, running calibration after calibration, certain, at each stage, that something so large and so absent from every simulation had to be an artifact of the hardware rather than a feature of the sky. It was not. The ribbon was real, and it had been sitting there, unnoticed, for as long as anyone had been able to look. A shape that large, hiding in plain sight above the sky over your own head, went unnoticed for a simple reason. Nothing built before 2008 was designed to see particles this specific, arriving from this precise angle, carrying this exact story about where they had been. You have slept beneath that ribbon your entire life without a single instrument on Earth able to tell you it was there. Every particle that made that first map possible had already been traveling for years before the mission ever launched, born at the edge of the solar system, long before the spacecraft that would finally photograph them had left the ground. The most widely supported explanation treats the ribbon as a kind of reflection. In the narrow slice of sky where our line of sight lines up at a right angle to the local interstellar magnetic field, particles get sent back toward us instead of scattering away, brightening that one band far beyond its surroundings. The boundary of the solar system acting, briefly, like a mirror tilted at exactly the angle needed to catch the light. It is an elegant idea, but it is not a settled one. Later observations found the ribbon shifting and dimming across just a few years, on a timescale tied to the sun's own activity cycle, meaning whatever mechanism paints this feature across the sky is not a fixed geometric accident, but something actively, continuously responding to changes in our own star in ways the leading model does not yet fully predict. Competing explanations exist, involving different populations of particles and different regions of origin closer to home, and none of them has been ruled out cleanly enough to end the argument the way the plasma density number once ended the argument over the magnetic highway, back when a single measurement was enough to settle things. Here's the question that keeps physicists awake. A structure bright enough to dominate an entire map of our solar system's boundary, discovered entirely by accident, still isn't fully explained more than 15 years after it was first seen. We found it before we understood it, and tonight, we remain closer to the first condition than the second, closer to noticing than to knowing. Every few years, a new paper claims to have finally settled the ribbon question, and every few years, a following paper complicates the claim again in the same slow rhythm that has defined this argument since 2009. That is not a sign of a field failing to make progress. It is what an honest, ongoing argument over real data actually looks like from the inside, before enough evidence accumulates for one explanation to finally, quietly, outlast all the others. Nobody currently working on the ribbon expects to be the one who ends it. They only expect to move the argument slightly closer to whoever eventually does. Consider what that actually means. A feature bright enough to be the single most striking structure in any map of our own solar system's edge, discovered by a mission that cost a fraction of either Voyager, and the honest, current state of the science is still closer to a working guess than a settled fact. Not because nobody has tried, because the boundary itself, once again, refuses to hold still long enough to be measured the same way twice. We still don't know, tonight, whether the mirror explanation is the whole answer or only the most convenient one so far, the one that happened to fit best until something better comes along. You can carry that one unresolved, along with the rest, into your sleep tonight. And that, unresolved, honestly, is where we're leaving it. For most of the 20th century, the shape everyone assumed was a comet. A rounded nose facing the direction the sun travels through the galaxy, and a long tail streaming out behind it, the way a comet's tail always points away from whatever it is passing. Every textbook illustration, every planetarium show, every popular image of the edge of the solar system drew that same elongated teardrop, tapering off for tens of billions of miles into the dark. But nobody had ever actually seen it. Then, in 2015, a team working from Cassini and Voyager data proposed something that unsettled the entire field. There might be no tail at all. Cassini's contribution came from an instrument built to study Saturn, not the edge of the solar system, but pointed backward across billions of miles. It could also register energetic neutral atoms streaming in from the direction of the heliosphere's supposed tail. And what it recorded matched no long, gradually fading plume. In this model, the Sun's own magnetic field, the same field that flips its polarity roughly every 11 years, reconnects and severs any long trailing structure almost as fast as it forms, leaving something closer to two rounded lobes, a shape one physicist compared to a soft croissant, folded back on itself rather than stretched into a point, a shape that reinvents itself in the same 11 years it takes to grow. Whatever the true geometry, it has never once finished forming before the Sun's own field flips again and starts the reshaping over. Other research groups push back immediately, defending versions of the long tail using different assumptions about how fast the interstellar wind moves past us, and how quickly the Sun's magnetic field actually reconnects out there. Neither side has produced a measurement that ends the argument. Both are working from the same handful of spacecraft, the same few crossings, extrapolating a shape for something roughly 200 times the width of the solar system, from data gathered along two thin lines through it. Here's what those numbers don't tell you. We have never seen the far side of our own solar system. Not once. Every image you have ever seen of the heliosphere from the outside, the rounded bubble, the streaming tail, the croissant, is an illustration, a guess rendered as fact for a documentary graphic. We are not being told the truth about our own address in the galaxy so much as we are being told the current leading guess. And the guess has changed at least once in the last 10 years, and may change again before this sentence finishes being useful. No mission currently funded is built to settle it. Doing so would mean sending a spacecraft out through the tail itself. A target nobody has agreed on the coordinates for. On a budget nobody has approved. For now, the true shape of the only home our species has ever had remains an open question, sitting on a shelf, waiting for a budget nobody has yet approved, and a spacecraft nobody has yet built. 5 years before either Voyager launched, two smaller spacecraft called Pioneer 10 and Pioneer 11 left Earth on trajectories aimed at the same outer boundary, carrying simpler instruments and far less power to run them. Pioneer 10 sent its last usable signal home in 2003. More than 3 decades after launch, from a distance of roughly 8 billion miles. Remarkable for its era, and still tens of billions of miles short of the wall its successors would eventually reach. But neither Pioneer lived long enough to confirm a single one of tonight's 7 discoveries. They proved the outer solar system could be reached and survived by a machine of that generation, and then ran out of power precisely at the threshold of the more interesting questions, handing an inheritance of curiosity rather than an answer to the 2 spacecraft that followed a few years behind them. Pioneer 11 fell silent even earlier, its last usable transmission arriving in 1995. Its exact current position now unknown to a precision better than a rough estimate, because no working instrument remains to confirm it. The 2 programs overlapped by design. Engineers who had worked on Pioneer moved directly onto the Voyager team, carrying forward instrument designs, trajectory calculations, and hard lessons about which components tended to fail first on a mission this long, lessons paid for in silence rather than success. Voyager did not begin from a blank sheet of paper. It began from the specific, itemized disappointments of 2 machines that had gone just far enough to prove how much farther there still was to go. Both Pioneers also carry their own small plaques, gold anodized and etched rather than recorded, showing the shape of a man and a woman and a simple map back to Earth. A rougher, earlier attempt at the same impulse that would later fill an entire golden record on the spacecraft that succeeded them. 2 small metal rectangles, mounted decades before anyone knew whether the idea of leaving a message for the dark made any sense at all, are still out there now, farther from home than the plaque's own designers ever expected to matter. Every discovery you have heard about tonight belongs, in a sense, to a relay race the Pioneers started and were never able to finish themselves. You are, in effect, the reason the race was ever worth running. By the time Voyager left Earth, the Pioneer program had already answered the one question that mattered most for what came next. That a small, modestly funded machine could survive the radiation belts of Jupiter, the cold of the outer planets, and years of silence between course corrections, and still keep talking? Everything discussed tonight assumes that answer as a starting point, inherited rather than earned twice. The plaque's etching had to assume, just as the later record would, that whoever eventually found it might share nothing with its makers. Not a language, not a body plan, not even a shared sense of which way was up. A successor mission, the Interstellar Mapping and Acceleration Probe, launched in 2025 specifically to build a sharper, faster updating map of this same boundary than the original 2009 survey ever could. But it will not resolve the ribbon question by the time this sentence finishes. Answers built from an instrument watching a structure this faint, this far away, arrive slowly. In years, not in nights. The new mission carries instruments roughly 1,000 times more sensitive than the ones that first found the ribbon in 2009, built specifically to resolve whether it is a mirror, a different mechanism entirely, or something nobody currently studying it has even proposed yet. It will take years of quiet, patient orbiting before enough data accumulates to say anything with real confidence. Somewhere in that slow, patient accumulation is the answer to a question the two Voyagers, for all they found out there, never got close enough to even properly ask. What it means, tonight, is simpler than a result. Somewhere above you right now, a spacecraft launched within the last year is quietly gathering photons born at the edge of your own solar system, adding to a map that has been wrong, revised, and wrong again for over a decade, and will likely be revised again before you wake up tomorrow, let alone by the time you happen to see whatever comes of it. The mystery is not abandoned tonight. It is simply still, patiently, quietly being worked on, the way the best and oldest mysteries almost always are. Its predecessor flew for over 15 years before finally being retired, having done its job, and then some, handing off an unfinished argument to a successor built specifically to keep the same question open a little longer, from a slightly better seat, with instruments its own designers could only have guessed at decades earlier. The scientists who will eventually publish the paper explaining the ribbon, if it is ever fully explained at all, are likely already reading through the first data this newer, sharper instrument sends home, without yet knowing which of today's competing explanations they are about to rule out. Whoever they turn out to be, they will be standing on a chain of machines and discoveries that stretches back to two spacecraft built when rotary phones were still standard equipment in most homes. Every instrument in this episode, from a magnetometer that almost failed to unfold to a satellite launched within the last year, has been part of the same slow relay. One machine measuring what it can, handing the unresolved part of the question forward to whatever comes next. Nothing in this story has ever been finished by a single spacecraft alone, and nothing currently flying expects to be the last one asked to try. Somewhere further out, a mission after this one is already being sketched on paper, by engineers who do not yet know which of tonight's 7 discoveries their own instrument will end up revising or confirming decades from now. Both Voyagers run on a generator that loses a measurable fraction of its output every year, decaying quietly since before either spacecraft reached the walls described tonight. Now watch what that decay actually does. One step at a time, power output falls. Engineers switch off a heater to compensate. A sensor near that heater drops below its rated operating temperature. Its readings grow noisy, then unreliable, then silent. Mission Control removes it from the daily downlink to save the power it would have cost just to keep listening to noise. That is not a hypothetical sequence, but it is the sequence. Engineers have already switched off instrument after instrument to keep the essential systems alive a little longer, including, eventually, some of the very sensors responsible for several of tonight's 7 discoveries. Voyager 2's plasma instrument, the one that measured its historic crossing directly in 2018, was already powered down by mission planners in 2024 to save the fraction of a watt it costs to run. Within the coming few years, by most current projections, there will not be enough power left on either machine to run any scientific instrument at all, only enough to keep a faint signal reaching home. Everything you have heard tonight was measured by hardware that is, right now, quietly running out. The 7 Discovery record explored tonight is not a chapter still being written by the Voyagers themselves. It is very close to the last chapter they will ever get to send. Engineers already know, roughly, which instrument will be the last one still working and which will go quiet first. They have known for years which sensor to sacrifice first to keep the transmitter alive a little longer, and which single measurement they are least willing to lose. Even the order of this slow shutdown was planned deliberately, decades in advance, by people who understood they would not be the ones deciding, in the moment, what to let go of last. Not a single dramatic failure. 1,000 small, scheduled ones. Each one chosen years ahead of the power, finally running out. Most of the team that built these 2 machines in the 1,970 seconds is no longer alive to see how the story ends. The people managing the shutdown today inherited both the spacecraft and the responsibility for choosing, gently, in what order, a 50-year conversation with the edge of everything finally goes quiet. There is no plan to bring either spacecraft home, no rescue mission, no way to add more power, once what remains is finally spent. Right now, tonight, both are still awake. Voyager 1 is well over 15 billion miles from the Sun. Voyager 2, on its slower path, trails at just under 13 billion. Both are still measuring something, however faintly, about the edge of the only home either of them has ever known. That will not remain true for very much longer. And almost nobody currently alive, including you, will be there to notice the exact night it finally stops. When the last transmitter finally goes silent, whichever year that turns out to be, both machines will keep moving anyway, carrying their golden records and their finished, unfinished record of discoveries into a dark that will no longer be listening back. But no mission currently funded will reach the same boundary again for decades. The interstellar probe described earlier tonight remains a proposal on paper, not a spacecraft on a pad, and even its most optimistic timeline puts a new direct crossing decades past the point where either Voyager will still be transmitting. Consider what that actually means. For some stretch of years, possibly decades, humanity will have no working instrument anywhere near this boundary at all. Not a worse view. No view. The 7 discoveries in this episode may simply be the whole of what our species knows firsthand about this wall, for longer than most of you listening tonight will be alive to see corrected. Now add the part almost nobody sits with. The engineers currently deciding which instrument to sacrifice next were, most of them, not yet born when Voyager launched. They inherited a machine, a mystery, and a shutdown schedule from people they mostly never met. And they will hand off whatever remains, silence included, to people not yet born themselves. The original mission control room from 1977 no longer exists in any recognizable form. The engineers who calibrated the magnetometer's boom, who chose the ribbon's name, who waited a year for a magnetic field to rotate, have mostly retired, or moved to other missions, or died, the way Ed Stone did, the way Gannett did, the way Sagan did decades earlier. Still, the mission has now outlived at least 2 full human generations of the people who ran it, and is being handed, piece by piece, decision by decision, to a third. That handoff is not a footnote to tonight's 7 discoveries. It is the reason any of them exist at all. No single career is long enough to watch a machine built in 1 decade, still redrawing the shape of the solar system 5 decades later. It takes a relay of people who never expected to finish the job themselves, choosing 1 budget cycle and 1 retirement at a time to pass it forward instead of letting it end. Somewhere in that relay is a scientist alive right now, early in a career that has not yet touched this mission, who will one day be the person deciding which of the two remaining instruments gets to keep its power a little longer, and which does not. They do not know it yet, neither did the engineers who first folded that magnetometer boom decades before it would matter. A 50-year argument with the edge of everything is ending, not with an answer, but with a slow, deliberate, scheduled goodbye, chosen years in advance by people who will not be there to hear it, any more than you will be there for whatever finally replaces it. Step back now, from the specific walls and specific years, and look at the shape of the whole argument. Every one of tonight's 7 discoveries was, underneath the specifics, the same event, a boundary, checked from a different angle, giving an honest but different answer each time. The wall 2 machines couldn't agree on. The sound recorded where no air exists. The highway that let radiation cross both ways. The boundary that gave way in days after 35 years. The second machine that measured what the first one's broken instruments missed. The region hotter than physics allowed. The ribbon of light no equation predicted. Not 7 separate mysteries. One single mystery examined 7 separate times by instruments that never once lied and never once agreed with each other completely. Go back through the list once more and notice what each disagreement actually cost somebody. The asymmetry cost 2 teams a search for an instrument error that was never there. The false alarm cost a community 2 years of premature belief. The vanished bow shock cost 50 years of confident diagrams. The magnetic highway cost Ed Stone a year of holding a headline back by force of will alone. The direct crossing cost Voyager 2's own team a long, careful wait before they trusted a number their sibling spacecraft could only guess at. The temperature reading cost an entire vocabulary, its comfortable meaning of the word hot. The ribbon still costs, 15 years later, anyone honest enough to admit the mirror explanation might not be the whole one. Every one of tonight's 7 discoveries was, in its moment, an inconvenience to somebody who wanted a simpler, tidier answer than the one the wall actually gave them. That reframes what terrifying actually meant. From the start of tonight's episode, not a monster waiting at the edge, not a hidden danger the 2 machines only barely escaped. The terrifying part, if there was one, was smaller and stranger than that. The edge of your own home does not hold still long enough to be measured the same way twice, by the same kind of machine, built to the same tolerances. Asking the same honest question, a wall that will not agree with itself, is not a flaw in the instruments, but it is the truest possible description of a boundary that was never a line to begin with, only ever a negotiation, checked from wherever 2 accidental threads of hard data happened to pass through it. A solar system, it turns out, is not a place with an edge. It is a pressure, holding a shape only for as long as something pushes back from outside, it just as hard. Hold that thought against everything measured tonight. The wind that never stops blowing outward from our own sun, the wider galaxy leaning back against it from every direction at once. Somewhere in the middle of that negotiation, held rather than bounded, your entire solar system and everyone who has ever lived inside it. Voyager 2's tour of all 4 giant planets. The flybys that produced years of images and readings feeding directly into tonight's later discoveries depended on a planetary alignment so rare it happens only once every 176 years. Jupiter, Saturn, Uranus, and Neptune lined up in a configuration that let a single spacecraft use each planet's own gravity to sling itself toward the next one, trading a fuel budget no rocket of that era could have carried for a sequence of gravitational assists nature happened to offer for free, for a launch window measured in months rather than centuries. A young engineer named Gary Flandreau noticed the alignment in 1965, more than a decade before either spacecraft launched, while still a graduate student calculating trajectories at NASA's Jet Propulsion Laboratory. Nobody had asked him to look for it. He found it doing routine trajectory work, checked the math twice, and then spent years helping convince an agency that a mission built around a window that specific, that far in advance, was worth the risk. Miss that particular alignment, and no version of this episode exists. Voyager 2 would have needed a separate rocket and years of additional flight time to reach each subsequent planet on its own, if it reached them at all within a single working lifetime, let alone a single spacecraft's operational lifespan. NASA had, at various points, considered a far more ambitious four-spacecraft grand tour to take full advantage of the same alignment. But budget cuts in the early 1,970 seconds reduced the plan to the two Voyagers actually built. A compromise that still, decades later, delivered every discovery this episode has described. Voyager 1 took a shorter, faster path past only Jupiter and Saturn, freed from the four-planet sequence specifically so it could investigate Saturn's moon Titan up close, a choice that permanently removed it from any possible flyby of Uranus or Neptune afterward. Two identical spacecraft, launched 16 days apart, split onto two different paths through the outer solar system, for reasons that had nothing to do with the discoveries this episode has described, and everything to do with choices made years before either machine left the ground. By the time both spacecraft finally met the boundary this whole night has been about, they arrived having seen almost none of the same things along the way. The next alignment, this precise, will not occur again until sometime in the next few centuries, long after you and everyone you have ever known is gone. Whichever engineers eventually get to use it will be working from a plan Flandreau sketched out by hand decades before any of them were born. Flandreau himself lived to see both spacecraft complete the tour his calculations made possible, and lived long enough afterward to watch them reach the boundary this episode describes, though he was not part of the teams that argued over what the crossing actually meant. He died in 2024, the same year as Ed Stone, two men who had spent much of their working lives on opposite ends of the same machine's timeline. One plotting where it would go, decades before launch, the other explaining what it found once it got there, decades after. Neither Voyager runs on solar panels. Past the orbit of Mars, sunlight grows too faint to power much of anything, so each spacecraft instead carries a radioisotope thermoelectric generator, a sealed container of decaying plutonium-238 that converts the heat of its own steady radioactive decay directly into electricity. No moving parts, no sunlight required, no maintenance possible. Plutonium-238 decays with a half-life of about 88 years, meaning the fuel itself has lost only a modest fraction of its total heat since 1977. The same isotope, produced in specialized reactors, that has since become difficult and expensive enough to manufacture that NASA now rations its remaining stockpile carefully across future missions. The bigger loss comes from the thermocouples that convert that heat into usable electricity, materials that degrade with age and radiation exposure faster than the fuel itself fades. Combined, the two effects cost each spacecraft roughly 4 watts of usable power every year, a decline so steady that engineers can predict, years in advance, almost to the month, when a given instrument will finally have to go dark. Not a single one of tonight's 7 discoveries happened on an instrument engineers expected to still be running when they finally recorded it. Each spacecraft launched with a little under 500 watts available, less than you likely used this evening to light the room you fell asleep in, enough at the time to run little more than a household appliance or two aboard a machine meant to reach 2 planets and stop. Today, decades into the decline, each machine operates on a small fraction of that original budget, carefully rationed across a transmitter, a handful of surviving instruments, and the heaters that keep the propellant lines and fuel from freezing solid in a place where the ambient temperature sits barely above absolute zero. But nobody at either spacecraft's construction in the 1,970 seconds expected the power to still matter 50 years later. The generator was built to comfortably outlast a 5-year mission to 2 planets, with margin nobody thought they would ever need to spend. That margin, and nothing else, is now the only thing standing between tonight's 7 discoveries and total silence. A margin that shrinks by roughly 4 measurable watts with every year that passes, on a schedule nobody can renegotiate. Every heater turned off, every instrument retired ahead of a true hardware failure, every year of continued transmission has been purchased directly out of a fuel budget calculated for a much shorter errand than the one it actually ended up funding. The plutonium itself will keep decaying for centuries after the last watt useful to any instrument has already been spent. The fuel will outlive its own usefulness by a margin far longer than the mission itself has lasted, quietly cooling toward irrelevance long after anyone is left to measure it. Every discovery you have heard tonight has been paid for, one measured watt at a time. Out of margin, an engineering team budgeted for a much shorter trip than the one it actually made. In 1990, with both of its planetary flybys long finished and every camera aboard scheduled for permanent shutdown to save the power they cost to keep running, Voyager 1 was given one final set of instructions: turn around and take a photograph of home. The request came from Carl Sagan, the same astronomer who had helped choose the contents of the Golden Record over a decade earlier, who had been pushing for the image for years against engineers who worried that pointing the camera anywhere near the sun risked damaging the optics for no scientific return at all. But Sagan won the argument. With weeks of power left on the cameras to spare, the photograph, taken from just over 3 billion miles away, shows Earth as a single pale point of light, less than a pixel wide, caught in a scattered band of sunlight across the camera's own lens, a beam of scattered light that happened to fall across the frame purely by the accident of the spacecraft's own angle to the sun that day. No visible sign anywhere in the frame that anything living had ever set foot there at all. Sagan would later write an entire book built around that one image, calling it the pale blue dot, arguing that everything humanity had ever fought over, built, or destroyed had happened on a point of light too small for its own camera, from 3 billion miles away, to properly resolve into anything at all. The cameras were switched off permanently within weeks of taking it, to save the power they would otherwise have kept drawing for images of a star field with nothing left to discover. No camera aboard either spacecraft has taken a picture since. Every image humanity has of Voyager's view from the outer solar system, and of Earth from beyond it, was captured before this episode's own boundary crossings ever happened, by instruments that were retired before the wall itself was even reached. You have never been photographed from where these 2 machines are now, and neither has anyone else who has ever lived. Nobody has, and after 1990, nobody ever tried again. The one picture taken of home from anywhere near this distance was captured decades before the discoveries in this episode, by a camera that no longer exists in working order, at the request of a man who did not live to see the boundary his own request had glimpsed the edge of. Every discovery described tonight happened after that photograph, using instruments that had nothing whatsoever to do with sight. Magnetometers, plasma detectors, cosmic ray counters, an antenna built specifically to listen rather than to look. Nothing you have heard about in this entire episode was ever seen. Every wall, every wave, every ribbon of light was heard, felt, or counted instead. Whatever the true shape of the wall beyond this boundary turns out to be, no camera will be the one to show it to us. The only eyes either spacecraft ever had were retired, deliberately, while they still worked perfectly well, decades before either machine ever got this far out. A command sent to either spacecraft today takes more than 22 hours to arrive, longer than it would take you to drive across your own country without stopping, traveling at the speed of light across a distance that keeps growing by roughly 1 light second every 20 hours. The reply, if there is one, takes another 22 hours to come back, meaning a single question and its answer cost the better part of 2 full days before anyone accounts for the time it takes a human team to actually read the numbers and decide what they mean. But distance is not the only cost. Only 3 facilities on the planet are physically capable of hearing either spacecraft at all. Enormous dish antennas in California, Spain, and Australia, spaced roughly a third of the way around the globe from each other specifically, so that as the Earth rotates, at least one of them always has a clear line of sight to wherever both spacecraft currently happen to be. The signal that finally reaches one of those dishes, after 11 billion or more miles of travel, arrives fainter than a billionth of a watt, weaker than the power it would take to run a digital wristwatch, spread across a receiving dish wider than a football field, just to gather enough of that faint signal to read. Both spacecraft now compete for that same scarce listening time against every other active mission in deep space. Newer probes with newer science, arguing for priority on antennas that were never built to serve this many spacecraft at once. The network itself is decades into its own aging process. Some of its dishes older than the mission they are still straining to hear. Every hour spent listening to a 50-year-old mission is an hour not spent on something newer, and every renewal of that priority has to be argued for again against people who did not build these 2 machines and did not choose, on their own, to keep listening this long. That same argument, in a different form, is the reason either spacecraft is still funded at all. Someone, every year, has to choose not to be the one who finally lets it go quiet. Now consider what a single answered question actually costs. Tonight, nearly 2 days of light alone, a fraction of a watt weaker than almost anything else these dishes are built to detect, and a scheduling argument won, once again, against newer missions with a stronger claim on the same limited hours. Every one of tonight's 7 discoveries travelled that same route home, arriving as almost nothing, on borrowed listening time, after a delay longer than the news cycle that would eventually report it. The conversation between these 2 machines and the species that built them has never once happened in real time. Not on the first day, and not tonight. It has always been a message, and then a very long wait, and then, eventually, an answer to a question the machine itself had usually already stopped wondering about by the time the reply came home. So here, finally, is what tonight's 7 discoveries actually were. Not one wall, but a negotiation, checked 7 separate times. A wind built into a bubble that leans harder on one side than the other, a foam of magnetic bubbles nobody predicted, a highway that let radiation cross in both directions before any instrument agreed a border existed. A boundary that gave way in days after 35 years of patient travel. A second machine that measured, directly, what the first one's broken sensors could only infer. A region that ran hotter than every model said it was allowed to. And a ribbon of light wrapped most of the way around us that still, after 15 years, refuses to be fully explained. The edge of the solar system was never a line you cross once and leave behind. It is the argument our own sun has been having with the rest of the galaxy for 4.5 billion years. A pressure, not a place, held only for as long as something keeps pushing back from outside it just as hard. The edge kept saying something different every time we asked, because the edge itself was never one answer. It was every answer we were given, honestly, from a different angle each time, the way the truest things in your own life rarely arrive as a single tidy sentence either. Somewhere out past both crossing points tonight, the wall is still moving, the field is still climbing, and a spacecraft launched within the last year is still gathering the photons that might finally explain the ribbon. None of it is finished. All of it is still, patiently, being worked on by machines that are running out of the power to keep answering, and by people who were not yet born when the question was first asked. In 1977, 2 machines left on an errand built to last 5 years. 48 years later, we've drifted with them past a wall that turned out to be dented rather than round, through a foam of magnetic bubbles nobody predicted, into a highway that let particles cross both ways before anyone agreed a border had been crossed at all. We've heard a boundary ring like a bell, felt it flicker before it finally held, and found a ribbon of light neither machine ever saw coming. You have never left the bubble you were born inside of. Not a metaphor. A real, physical wall, built from the breath of our own sun, dented on one side, humming faintly on every side, holding its shape only because something out past the edge of everything keeps leaning back just as hard. You have spent every night you have ever slept safely on the calm side of it, without needing to resolve a single one of its 7 disagreements with itself. If your eyes feel heavy, let them close. The 2 machines that found all 7 of tonight's discoveries are still out there, still sending their faint signal home across billions of miles, still doing their patient, fading work, whether you are awake to hear about it or not. If this felt like home, leave a comment when you wake up. And if you're still here, still drifting at the edge of sleep, the next chapter is already waiting. The universe will still be here when you wake up, so will we. Good night.